This week we take a look at the application and physical layers. The application layer, the software packages that you get to run on the application layer. These packages are the reason why we have the network in the first place, because you want, as you perform the productive work or the meaningful work using these applications, you want to be able to share this or transmit it over the internet or the network. Um, the application architecture is the way in which the functions of the application layer software are spread among the clients and servers on the network. Think back to last week when we were talking about the different networks uh, that we have, and so you may have computers that are, you definitely have computers that are geographically interspersed, and you want to be sharing some data, um, and the architecture will determine how uh, the functions are spread out or laid out among the clients and the servers. The work done by any application program can be divided into four general functions. The first is data storage. Most application programs require data to be stored and retrieved, whether it is a small file such as a memo produced by a word processor or a large database such as an organization's accounting records. The second function is the data access logic, the processing required to access data, which often means database queries using maybe structured query language. And then the third function is the application logic, which also can be simple or complex depending on the application. Then finally, the fourth function is the presentation logic, the presentation of information to the user and the acceptance of the user's commands. All these four functions, data storage, data access logic, application logic, and presentation logic, are the basic building blocks of any application. And when we talk about application architectures, we are looking at how these functions are spread among the clients and servers. The first option that we have here is a host-based architecture. This is the first data communication architecture that we had back in the 1960s, and with this architecture, all of the performance of all these functions, the four functions that we just identified, which are the data storage, data access logic, data application logic, and the presentation logic. All of that takes place at the server, and the architecture or the client simply receive messages, and it's not even a client in the setup. What you have are called terminals. Then you have a second architecture, which is the client-based architecture. In this format, the client and the client performs most of the functions, and this is what we have with most local area networks, where you have what are called fat or thick clients, where much of the processing actually takes place at the client side, and then on the um, server side you may have mostly data storage. The third option would be client server architectures. The client-server architecture, it is a setup where functions are shared between the client and the server. And the idea here is to balance the processing between the client and the server by having both do some logic or some processing. This is the most common type of architecture that we have with most local area networks. And what we have been discussing here, the client-server architecture, is actually a two-tier architecture, in the sense that you have the client and the server, and the processing or the application, the functions of the applications are balanced between the two. Or you may also have a three-tier architecture. With a three-tier architecture, you have three sets of computers that are involved. And the first computer could be a client, which is responsible for the presentation logic. And then you may have an application server, which would be responsible for the application logic. And the third set would be say a database server, and this is where the data would be stored and queried from. So with with the three-tier architecture, the functions are spread across these three sets of computers. And n-tier architecture, this is simply to say you will now have more than three. It could be 4, 5, 6, depending on how the setup is actually made. For example, if you have a 4-tier, what you may have would be a client or personal computer on which you have the presentation logic. And if we were to use an internet-based application, the second tier would be the web server, where you have the application logic, and the application logic could be spread across multiple servers. And so you would have another server maybe responsible for a specific set of algorithms, and that would be contacted whenever there's a need for processing, the set of instructions. Then the fourth tier would be a database logic. So a variation of these here could be actually made to where you have any number of tier architectures. And the idea really is to balance the processing or the functions for the applications. This gives way to the idea of thin versus thick clients. When you have thin clients, these are personal computers or workstations which have little to no application logic, and so they rely on the server for much of the processing. Some workstations in some networks would make sense for employees that do not necessarily have to do heavy processing, and so you simply have a workstation and it's relying mostly on a server somewhere. The internet can provide such an architecture where on the client side all you have is the presentation, and all of the processing is taking place on the server side. The opposite of that would be The opposite of that would be thick clients, and with a thick client, um, or if not most of the application logic resides on the client side. So these personal computers tend to, or workstations tend to have more processing power, and so only rely on the server for data storage or other specialized processing. You also have a peer-to-peer architecture. Peer-to-peer architectures are, these are the very oldest architecture there is, but their modern design became popular in the early 2000s with the rise of the P2P file sharing with such providers as Napster. With a P2P architecture, all computers act as both a client and a server. Therefore, all computers perform all four functions. A quick recap on those: you have the presentation logic, application logic, data access, and data storage. With a P2P file sharing application, a user uses the presentation application and data access logic installed on his or her computer to access the data stored on another computer in the network. With a P2P application sharing network, um, other users in the network can use others' computers to do to access application logic as well. So there's a lot of sharing of files and even processing capacity. Some of the advantages include that the fact that data can be stored anywhere on the network, and it is very resilient to failure. If you have access to other computers that you can actually use for processing, then should any of the computers that are on that network go down, what it means is your options are, you have a few options that are available for you. But the disadvantage is when huge amounts of data is involved, it becomes difficult to actually locate specific records because there isn't any indexing or any the processing power for some of the machine computers that are actually on that network may be limited. Then of course there are security concerns. If everybody has access to everything, then you can't guarantee any security there. In terms of what to consider as you uh, decide on an architecture, of course, cost is a factor. The cost of servers, clients, and circuits. Mainframes tend to be very expensive, uh, but terminals or personal computers are not as expensive. But what it means is you have less processing power. But depending, you have to look at other factors, the kind of work, the number of employees, and who needs access to computing resources. Then you also have development cost. It's also part of the criteria that you have to look at as you decide on an architecture. This has to do with development. Remember, we were talking about how you have the application logic in you have the presentation application logic and the server. The more separated out these um, functions are, the more money is going to cost to actually develop a solution like that. Then you also want to look into scalability. What this means is if you have an application that has been written to What this means is how many more uh, users, or how many more users could you add on to uh, actually take advantage of the resources, and the system won't scale down, degrade in terms of performance. And generally, mainframes are not going to be as scalable as PCs or personal computers. Examples of applications, the World Wide Web, email, file transfer, uh, video conferencing, and instant messaging. Later on, as we talk about the different internet technologies, you'll find that the protocols are actually developed around these applications. We will now look at the physical layer, the second layer. This includes network hardware and circuits. Network circuits can either be, those are the physical media, for example, cables, and special purpose devices such as routers, bridges, and hubs. And these circuits can either be physical or logical. The word circuit has two very different meanings in networking, and sometimes it is hard to understand which meaning it is intended. Sometimes we use the word circuit to refer to the physical circuit, the actual wire used to connect two devices. In this case, we are referring to the physical media that carry the message we transmit, such as the twisted pair wire used to connect a computer to the LAN in an office. In other cases, we are referring to a logical circuit used to connect two devices, which refers to the transmission characteristics of the connection, such as when we say a company has a T1 connection into the internet. In this case, T1 refers to not to the physical media, but rather to how fast data can be sent through the connection. Often each physical circuit is also a logical circuit, but as you will see in in chapter 2 of your text, there are different ways the data can actually be transmitted. You have multiplexing, for example, as one method of actually transmitting the data. The types of data transmission that are available are analog and digital. Analog is used for telephone communication, sound waves, and it is it takes analogous to say voice. It is sinusoidal. Uh, in that's how it is represented, and the values can take any possible range. If you can envision a sine wave which goes up and down, and so the actual values can be on any on any of those on any of the positions within the wave. On the other side, you have the digital data transmission. This is what computers produce, uh, the binary data, and it is a series of zeros or ones, which can also be represented by either an on or off position. So the different data that we looked at can also be transmitted in those two different ways. You have the analog transmission, which is used for TV and radio. Then you have digital transmissions. What this means is that data is transmitted in discrete square. Uh, you have high and lows, up and down, or off and on, whereas on the analog you have that sinusoidal transmission. Data can be converted for the purpose of transmission, and once it gets to the destination, it can then be converted back to how the device can actually decode the data. So a modem is responsible for modulating and demodulating the data as it is transmitted. As you are probably aware, the digital transmission option has more advantages than the analog transmission. Some of these advantages include that digital transmission produces fewer errors. Remember, you have the two positions, 0 or 1. So even as the signal is weakening, it is much easier to boost it back up to its original and accurate form. Whereas with the analog transmission, the actual value could be on any position within that wave, and it is much difficult to reproduce, or it is prone to error. It permits higher maximum transmission rates, so you have options like optical fibers that can transmit digital data at higher rates. It is more efficient. Most devices use digital data anyway, so if it doesn't need much conversion before it is packaged for transmission. It is more secure, that is to say, it can easily be encrypted, and also it is easier to integrate with different data types. For example, it can represent voice, video, and data effectively.